Hi, good morning. I'm the chairman of this session. So I'll introduce our jury in Chinese. 参加一大学初中，师大附中李国汉老师，台师大武焕宇老师，海洋大学陈振宇陈老师以及高雄大学林俊忠老师，请鼓掌。Every team have to introduce themselves. From the reporter, please. Captain.
Okay, my name is Andrew, the captain of the laboratory team. This is Hans, this is Howard, this is Bernie, and this is Danny. Thank you.
Okay. So with the opponent.
My name is Ethan. I'm the captain from Indal Freshwater from Indal High School. I'm Ethan, Alan, Michael, Justin, and YC. Thank you.
From the reviewer.
Hello everyone, we are Team Insulator from National Geographer Senior High School. I'm going to present my teammates 黄六杰、朱伟珍、陈玉安、杨彩文。
Okay. So the last one is on Herbert.
Hello everyone. We are Team All Nighters from Evan American School. I'm Captain Ethan Wu. This is Sean Bay, Lim Gu Tan, Hamilton Go, and Isabel.
Okay. And so let's start the order of the speech. The first stage is the opponent challenge the reporter for the problem. In 1 minute.
I say a challenge for requirement element, public stroke.
Ready?
Reject.
Okay. And now the problem working and the problem part is available.
Challenge for 45 paper markets.
Accept.
Okay. So the reporter said problem number 5.
Yes. Yes, 5. Thank you.
Everything right on the divider on the breadboard. Okay, so the problem can start.
Well, good morning, dear judges and fellow debaters. I am a reporter from the Laboratories team, and today we are going to report on problem number 5, ping pong rock. Here is our outline of my report. Okay, let's take a look at the problem statement. The ping pong ball is placed on a container of water. So when the container is dropped, the ball gets ejected and launched to a great height. What maximum height can you reach with up to 2 liters of water? So from this, we can get that the point of this experiment is the liters, meaning the mass of the container that is having water, and the maximum height, which the ball gets launched. And this is our observation of the phenomenon. As you can see, when the container drops to the ground, the ball gets ejected to a height, and this is our animation. Well, this is actually called Worthington J, which we'll discuss later. Okay, so we have this video, so we put it into Tracker and Google Sheets, and we do an analysis of the phenomenon. From the HT graph, we can find that the ball doesn't touch the bottom of the cup. And from the VT graph, we can find that the time when the ball bounces is close to 0. So, in experiment 1, we want to find the correlation between water mass and bounce height. So we need to do some reasoning and deductions for our theory. Well, because it doesn't reach the ground and it's something like this, so there is no buoyancy in this phenomenon. So we assume that surface tension is the main forces in play in this experiment, because forces are too complicated to consider. So we discuss energy instead and assume that this is an elastic collision. So our theory is the conservation of momentum under elastic assumptions. So this is actually the relative movement of the ball and container with the water. And this is the conservation of energy, with this being the total energy via release, and this being the total energy when the ball bounces. So from our theories, we can get this H bounce and H initial relation, which is a formula right here. So from the formula here, we can draw a graph with GeoJoule, and we can see a convergence at about 9 right here. So we want to predict that as the mass ratio increases, the height ratio will also have a convergence. So we have our manipulated variable, the mass of water, meaning changing the mass ratio, and the control variable, the mass of cup, the release height, and the ball. And the response variable is the bounce height, which we can test out the height ratio, the bounce and release. Okay, here's our experimental video. As you can see, this has the smallest mass, and it gets ejected to the smallest height. This has the medium amount of water inside, and gets ejected to a medium height. And this has the most water inside, and it gets ejected the highest. So this is our experimental design. We stabilize the release angle to ensure our experiment accuracy. So that way we use a cylindrical tube to stabilize the falling movement of the container. So we use a stick to place something by hand and pull it out to release. And we make holes on both sides of the stick to make it go free. And that's what this way, the release height will stay the same throughout the experiment. And this is our experimental setup. We use 40 centimeters, and we have the relevant parameters right here. This is our experimental data. As you can see, as the water volume increases, indicating a higher mass ratio, the bounce height converges right here. So we put this into the H ratio and mass ratio graph, and we can see the convergence of height ratio as mass ratio increases. Well, the tendency is correct. We cannot get an exact formula since there is energy loss in this experiment, and the fluid motion inside the container is chaotic. So, in our experiment 2, we want to find the correlation between release height and bounce height, and discuss about Worthington J in the phenomenon. So we also did some reasoning and deduction for this experiment. We observed that this photo, and we think that Worthington J, caused by the collision, is the main factor of this experiment. So collision and surface tension causes the Worthington J to happen forming an air cavity. So it ejects the ball, and thus the Worthington jet is formed. So the discussion of Worthington jet. There is collision when the ball gets under the water, and the air cavity is created, building up potential energy, forming the Worthington jet and ejecting the ball. Well, this formula is from Navier-Stokes equation with a research conducted by MIT. So we just use it here. We can find the correlation of Fr squared with the Weber number. So we consider the ping pong ball as a hydrophilic sphere, where the wetting angle is below 70 degrees. So the Weber number of the Worthington jet is said to have a proportion to the Fromm number squared. So we postulate that the ball launches only due to Worthington jet caused by the collision. The bounce height will be proportional to the release height, as the release height here. And there is an initial jet speed squared right here. So this is a schematic diagram. Because we know that the bounce height is proportional to the release height, which is actually the same to the assumptions that we have with elastic collision. We want to find when we have different release heights, what will the bounce height be? So we manipulate the release height, and we want to respond variable is the bounce height. That way we can find that the height ratio will stay the same. So this is our experimental results. For the slope, we can calculate the coefficient of restitution of this collision, as the R squared is 0.9877, proves that Worthington jet is the cause of this sludge. Well, because the error bars are so big here, we assume that there are maybe other chaotic fluid flow that may integrate with our experiment. So we analyze the derivation, and we think that capillary waves caused by surface tension may cause energy loss, and these waves travel around the boundary of the liquid with their surface tension as the restoring force of the capillary waves. This might be the cause of derivation in the experiment, as the error bar is very big. So, from the slope here, we can find the bounce height and release height ratio. With this ratio, we can calculate the coefficient of restitution. So we put in, so this is actually the coefficient of the ground and the container. And we did some experiments to find out that the coefficient of the ground is 0.35. So now we want to measure the coefficient of water. With a bounce and release ratio, we put 0.771 inside of this formula, and we can calculate the coefficient of water as 0.391. So this formula of coefficient of restitution is actually calculated with the relative motion before and after the collision, as the relative motion is the different side and the same side in these two formulas. So in experiment 3, we want to discuss what will happen with different containers with our qualitative experiments. So this in our experimental setup, we change the different containers in this schematic diagram. And the control variable is the mass and the fall height. And the response variable is the bounce height, which we can find the height ratio. And this is our experimental setup. We have a plastic bottle, a big plastic bottle, an aluminum container, and a gallon milk bottle. So, a small cup concentrates energy, which increases energy efficiency, indicating a higher launch. Like the small plastic bottle here, it launches higher, and a big plastic bottle launches not as high. And containers that are easy to deform conserve more energy, as less energy is consumed by the container. We can see that in the aluminum bottle, where the aluminum is hard to deform, meaning that many energy will be lost in the volume process of the container. So, to our conclusions, when will the maximum height happen? I know the problem statement talks about trying to find the maximum height, though we cannot because the release height and the bounce height actually has a proportional correlation. So we only can find a maximum height ratio when the water is close to 2 meters. We can see the convergence of like here. So we can assume that when the mass increases to a very substantial amount, the ratio doesn't change very much. So under ideal conditions, we can use our coefficient of restitution to calculate the height ratio, which could be up to 9, or same as the model we made from our elastic collision. However, if we calculate the energy loss, the ratio will be much smaller. So we have our ground coefficient. We put it in the formula. And under certain circumstances, we let the water, E-water, meaning the coefficient of water, to get to what? Meaning that if there is a highest possible coefficient of E-water, as when the smaller cup concentrates energy, we can maybe make the cross-section area so small that it gets potentially equal to what? Meaning a perfect energy transition, giving us a maximum type ratio of 2.89. So, to summarize our report, in the first part, we discussed the phenomenon using VT and HT graphs and ruled out buoyancy as the ball doesn't touch the bottom of the cup. Well, in the second part, we went over the energy transfer in collision and created a mathematical model. Then, we did an experiment of different mass ratio to prove that the tendency of convergence is correct, as it converges as 2. But the theory is not, so we can see the energy loss right here. And for the third part, we did a detailed discussion about the collision and found out that Worthington jet is in fact the main cause of this experiment. However, Worthington jet is caused by collision, meaning that the convergence will be correct as well. Then, we did another experiment of different release types to prove our theory. We can calculate the coefficient of restitution of water. In the fourth part, we went over different containers and discussed how containers affect with the energy transfer. And at that, we can make an educated guess that the biggest height ratio possible is 2.89 when the cross-section area of the container is small enough to make the E-water potentially up to what? Okay, here is our reference. Thank you.
So it's time to move on the friction of the opponent to order and answer.
So, you just say you don't consider buoyant force in your experiment, is that correct?
Yes.
Okay. And so in your experiment 3, you use different material of the container, right?
Yes.
And do you consider that they have a different shape?
We consider that in the
Yes or no?
yes.
So do you consider water viscosity and air resistance in your calculation?
No. We ruled out air resistance and viscosity.
And so throughout the experiment, do you make sure that your ping pong ball stays in the middle of the container?
Well, no. We did a lot of experiments and made an error problem.
So do you make sure that the contact angle of your container and the floor is controlled throughout the experiment?
Yes, with the cylindrical tube, we just showed earlier.
So you, as your demonstration videos, you drop the ball with your hands. So do you consider that hands might?
Well, we actually drop our containers with a stick, and the observation video is actually done in the early stages of our experiment.
I'm sorry.
The observation video is done in the early stages of our experiment. And the later we experiment, we use the stick to go over the container and then it drop out here.
And that's all.
Okay.
Thank you.
It's time for conversion. 3 minutes.
honorable judges. This is Alan from Team ND Fresh, and today I'm going to opposing problem 5, ping-pong rockets. So here's the problem statement, and the reporter's main focus is on the mass of the water and the initial release height and the types of container. So here's the summary for their reports. So in their theory, they use surface tension, conservation of momentum and energy, and they explain the phenomena within the jet. And in the setup, they use cylindrical tube container to make sure that the balls falls vertically, the container drops vertically. And the parameter is the mass of the water and the release heights and types of different containers. So their advantage is that they have great organizations and they show very good control in their reports, and their explanation on their results and theory is great. And our suggestion is that more direct conclusion of your analysis and a connection between the observation video and your experiment. And here's the points that I want to discuss. So first of all, you didn't consider buoyant force in your experiment.
Well, we ruled out buoyant force because when the ball enters the surface of the water, it is like a membrane-like structure, and the water is not inside the water, but goes through like this, the membrane-like structure. So there is no buoyant force inside of this phenomenon.
In your experiment, you explain this phenomenon within the jet, right?
Yes, the collision caused the working jet.
Yes. And so, please turn to the demonstration page.
Working
Okay.
jet.
Yes. That's what. So, right here. So, have you considered the depth of the water goes under the depth of the ball goes under the water into your calculation?
Well, from our theory here, the depth of water doesn't matter unless it hits the floor of the water. And from our analysis of phenomenon here, we can see that it doesn't hit the bottom of the water, meaning that the depth of the water didn't really matter in our theory and our experiment.
So, as long as the ball didn't reach the bottom.
Yeah, because if you hit the bottom of the container, there will be a normal force. Not that happens.
And so, could you please send to your experiment?
Which one?
Experiment 3.
Experiment 3. This?
Yes.
What do you want to see?
The showcase of the container you choose.
Okay, showcase.
So, as you picture, the shape of each container is not exactly the same, and as well as the radius of them. So, do you think that
Well, we are doing a qualitative analysis, and we're trying to define the characteristics respectively. However, we don't have any quantitative numbers to prove our theory, but we have a perspective. We can see the distinctive differences in different containers.
So there's different radius of your container.
Well, we didn't really measure the radius of the container because we're only trying to look at the characteristics of different containers' differences, respectively.
But that's a factor that might.
Well, I think this experiment is more like an observation of what will happen if there are different containers, and not to make a theory or anything like that. So we don't really have any numbers. But we see these just to explain our theories. Like the smaller cup consumes energy, and the deformation also conserves energy.
And so, how do you define a small cup?
Well, we can't not necessarily define a small cup because we are looking at this respectively. We just trying to analyze the characteristics of these 4 cups and see what the experimental results have a correlation with the analysis.
I mean,
Characteristics.
as you mentioned, the smaller n is referred to the smaller of the mass of the container, or
A smaller cup is the smaller area, cross-section area of the container. Like a plastic bottle and a big plastic bottle, it really has a different area underneath. But we didn't calculate the area because we're doing only a quantitative measure.
and so I'm asking if you take the radius of the container into consideration, because I think larger cross-section might cause larger water disturbance.
Yes, you mean that capillary rates that we have just talked about earlier, when you travel the boundary of the liquid. And when the cup increases, there will be more energy loss caused by this. Yes.
So I would like to ask if the radius of the container is smaller, and do you mean that the energy? It means the energy consumption is smaller, so the ball might eject to a better height.
If the cup is smaller and the mass stays the same, is that what you're asking?
Yes.
Okay, the mass stays the same and the area is smaller. The energy gets more concentrated, and meaning that there will be less energy loss. So it will get bounced up to a great height.
Okay. So
Well, of course, this is a little bit uncertain because we only have like 4 different models here. So in the future, maybe we can do more experiments to analyze the phenomenon. So that's about it.
So could you please turn to the mass of the water experiment?
So which one are you referring to?
This one.
Do you want to see our theory or
The photos.
the photos? The data or
This one.
okay, this one. You want to
Have you control the amount of water to 2 liters, right?
we cannot make the water up to 2 liters because the container cannot hold that much water. However, we can see a convergence as the mass increases. So we assume that when there are 2 liters of water, it is still, the height is still about here.
But here comes the problem. So as you mentioned, the more the mass of water is, the higher it gets, the higher the ball gets to, right?
Yes, but there will be a convergence, meaning that it will converge at some line here, and will basically stay the same when the mass increases more to a bigger magnitude.
Oh, so what's but as you increases the amount of water, so you have to have a larger container, right? And
You don't really need to have a larger container, you just need to have a higher container. But yes, what you said would happen if we have a bigger container, we can have more liters of water inside of the container. And if we want 2 liters of water, as the problem statement has stated, we probably will need a bucket to hold the water. However, I think that with the container is too big, there will be too much energy loss and making our experiment hard to consider.
so, can you show me your experiment data graph?
This
Yes. So do you think the trend will goes down as the whatever increases as just as you say, the increase of the cross section, the more energy consumption?
So you said, so what are we talking about? You want to say that if there is a different cross-section area,
No,
the
I mean,
height will go down.
as you say, may I use the blackboard?
Yes.
So as you say, the trend of the massive water and the river height goes like this, right?
Yes, there will be a convergence.
So my question is that if you, as you mentioned, if we have to do 2 liters of water experiment, we have to use a bucket, right?
Yes.
So there must be a large consumption due to the cross section.
So instead of bucket, maybe we can use a container that is very high, so low cross-section area. That way we can have the same amount of volume. Maybe consider that we make a container so small and have the ball right here. And this is very high. Well, however, this is almost impossible to do in reality. So we can only make predictions about what will happen when there are 2 liters of water. We predict that there will be a convergence, and the height ratio basically stays the same.
But just as you mentioned, so if you use a container like this, and so well the ball goes like deeper.
When the ball, well, I think the deepness of how the ball enters the water is determined by the velocity of how the ball enters the water, which is also determined by the release height. So if we control the release height to some extent, maybe it will penetrate and hit the ground or something like that. And also, according to our theory, the depth doesn't really matter.
Could you please turn to the page of your experiment video?
You mean this page?
The 3rd video. Could you show that again?
In this video.
So as you see here, while the ball is ejected, the ball touches the tubes, and have you taken that into consideration?
Well, because the velocity is, well, of course it touches the tube. But because I think the problem statement is referring to the maximum height. So when it touches, so we assume that this is also in an elastic condition. When the ball touches the cylindrical tube right here, we assume that it will bounce off like this with the same velocity upward, meaning that this won't affect the horizontal height, as if there is no tube, it will bounce here. And this is only to make the experiment more observable and make it more stabilized for observation.
But I mean, as your demonstration video shows, your surgical tube is made of plastic, and as the ball touches, the tubes deform. So to take that into consideration.
We didn't take the deformation of the cylindrical tube into consideration. Well, that's a valid point.
So I think so what you say here is not it's not fit in your experiment, since your surgical tube is made of plastic, so the ball won't go like this.
Well, it will to some extent. There might be some energy loss, but we didn't take that into consideration, as we mean that it is very big. Also, the chaotic fluid motion actually causes much more error in this experiment. And we did a lot of experiments to prove our theory.
Time is up.
Thank you.
So we first discussed about all the volume force, and they say that volume force doesn't really matter, and there's no volume force in the experiment. And so I asked about the experiment 3, the different shape of the container might affect the experiment result. And the reporter says that they only focus on the quantity of the heights, so they will improve their experiment. And we talked about the radius of the container, and we both think that the bigger cross-section of the container might cause energy consumption to the experiment and affect it. So,
Okay. two of the review. Please remove your mask. Thank you.
I also like to ask both of you and why the ball can reach a greater height in the container of water.
Sorry.
Why the ball can reach a greater height in the container of water?
So just as the reporter says, is caused by working ingest, which is related to the
And in what condition will make the ball to fly height?
Well, when the mass reaches to converters and the containers area, cross-section areas will have a higher energy concentration rate.
Okay, and how about you?
So as the report says, the more initial height it is, the ball will get launched to a greater height, but there's a limitation. So I think the limitation is quite what it is.
Okay, so next, which one do you think affect the result of the water volume over the drop height?
Well, both of them affect the experiment respectively.
Okay, and which one do you think will?
Well, if the mass is up to some magnitude extent, the effect will be converged. That it doesn't really matter, and the height is always a linear number.
So I think the initial release height is more important than the mass of the water since as a
And I want to add the reporter, and you mentioned about elastic closure,
Yes.
and but elastic closure can only be used in low energy loss. So do you think it's the formula is yes?
Well, I think we use the formula only to observe the tendency because
Yes. Okay.
of the fluid motion is lost.
And for mass, do you think the uneven bottom of the container will affect?
Well, it certainly will affect the experiment, but we have chosen a good surface and we put a piece of paper under the container.
How about you? The uneven bottom of
the uneven button of the container definitely affect the experiment since the different.
And do you think the oscillation of water is important always during the experiment? The oscillation of
We ruled out as energy loss with the chaotic fluid flow as it is impossible to predict.
so do you think it will affect or not?
Well, of course it will affect, so we did a lot of experiments to rule it out.
Just as we discussed, the larger this radius of the more oscillation, so more energy consumption, and that might affect the experiment results.
Okay. 2 minutes for preparation. For review.
to the relevant parameters that have a maximum height. And here is the review of the resource. And in his theoretical and model, they talks about the conservation of momentum and the mechanical formula of the collision process and the jet theory. And for his first issue, he connected with the moment accuracy, and for his theory can only be used in ideal situation. And he didn't consider the factor to establish the model. And in experiment, he talked about the collision of rather and ball and mass of the water and the different containers that of the different material and different ingredients. And he might demonstrate on the slide and explain the experiment process thoroughly and well in investigation of the water jets. But she later for the parameters which I think is adding more to observe this formula and might have error in the experiment process because there is something error in his data class and didn't consider enough control variable. And in data analysis, they have this data and clearly explain the connection of theory and data and organize the result of each parameter. But error bar is too big and didn't analyze the error well and only had a result of imaging check and doesn't do the anything from the problem statement. And for the review of the points and in short question, and they talk about the shape of the material and the experiment process and resistance and consideration of the points. And he mentioned that some points that the reporter didn't talk about good time management. He took two books at the experiment process and then mentioned about the virtual model. And in discussion, they mainly talks about the force by X on the ball and the formula of water and the result of changing the mass of the water. And she points out the difference of the theory model and precautions and connect with the short caution. But he lacked a discussion of the law being too big, and he didn't express his own opinion. And for the key questions, the opponent asked about do you consider the points forces an X on the ball, and the reporters say no. And in our opinion, we think the points is important, but the reporter didn't consider it. So I think it may be reason why the sheet track will be has the error like that's big. And for next question, the opponent asked about do you think the ball toss on the experiment setup will affect the result? And the reporter answered might be the reason why the error is too big. And I think it was really important because it will affect the result, like the frequency of the container of the yes. I asked why is the better to make the ball to fly a square time, and I think the water and both of them agree with it. And next question is which do you think affect the result more, the water level or the height? I think it's because of the water level because the mass of it will affect the force directly while the height not to be that direct and which content yes. And then they think the reporter says it's both and the opponent says height. And for the missing points, they didn't about the oscillation of the water and both of them think it's important. And for the missing point, for the reporter didn't mention how the pressure waves are formed and didn't investigate any convergent degree. And while they have mentioned in their report, but didn't investigate and didn't have the connection between theory and experiment data.
Okay. Before the
I am a reporter from Team Navigators, and this is the concluding remarks of my report. So for report summary, we did the observations of a ping-pong ball, which is ejected out by the warping engine. And the theory applied is the conservation of momentum, energy, surface tension, which cause the warping engine. And Navigators shows equations for ground number, river number, and the coefficient of restitution we use to find the maximum height ratio. And the convergence between the height ratio and mass ratio, I think, is the most important part of our report. Our variables is the volume of water, the release height, and capsule container, which we did quantitative characteristics analysis. So for opponent summary, the opponent asked about how buoyancy is formed, how the buoyancy will affect the experimental results. I would say that the buoyancy has little to do with the experiment, as the water is like a membrane-like, and there is no penetration of ping-pong ball into the water. And air resistance and viscosity, well, this is a valid point, and we should have considered this in our theory. The ping-pong placement secured in the middle or not. well, we try to make it secure in the middle, but however, this is a part of our derivation in our experiment. The contact angle stabilized by what's commonly explained. This is stabilized by the cylindrical tube when the ball is falling. And the shape of radius of containers will certainly affect experimental results. And the trend line will have a convergence between height ratio and mass ratio. So for the discussion summary, we clarify the things that we didn't consider, like aerosolence and viscosity, and different factors that affect the bounce height, like the cross-section area, the mass, and basically the convergence. So we compare our theory and our data. Our formula isn't correct, although the tendency is correct. And we talk about how increasing water mass and what will happen with the tendency. Thank you.
Time to our jury. Any questions?
Yes, yes.
Any questions? Yes, please.
I have one question about for the reporter. When you measure the height of your container and water, did you just measure from the bottom of the container, or you consider the center of the mass? Because different water and different container, your center of the mass is different. Yeah.
We consider it at the bottom because when it bounces, the ping pong ball will assume that it is at the water surface. So we want to control the height. So making it, let's say if we consider the bottom, the height of the ping pong ball is big H plus by small h of the water mass. And when it bounces, the container on the ground has a small h. So when big H plus small h minus small h, when it bounces, the h will stay the same, and we can make an analysis of the phenomenon through the experiment.
Yeah, I can understand how you did the experiment, but according to the potential, the gravity, we should consider the center of the mass, right?
We didn't consider the center of mass because we're trying to analyze the ping pong balls.
Yeah.
But we should have taken it into consideration.
Another please.
So I also like to ask a question reporter. So from your theory, it seems like you only consider the rigid body in the sense that it is a solid state, and when you twist it or rotate it, you won't change its shape. Okay. And however, the water should be liquid. So I just would like to ask how this non-uniform. I will suppose the way you solve the question would be non-linear, or that it would have some non-uniform property inside your theory. And how do you consider this?
Well, of course, there are problems with our theory. We should consider the water as a fluid. But however, in our theory, we can observe the tendency. We maybe need to take some effects of fluid into account, and it's probably the part of derivation in our experiment.
Any more? Okay, so it's time to score it. Change. Please wait. show 7, 8, 9, 8, and 6. Opponent. 6, 7, 5, 6, and 6. Finally, for review. 5, 7, 8, 6, and 7.